take a moment to read through this problem. We're going to do a couple of example problems here. In this problem, let's begin with what we know. We know that the mass of collar A is equal to 20 kilograms, and that the counterweight B has a mass of 10 kilograms. And then we know that some force is acting on A with a magnitude of 500 newtons in the downward direction. We know we're going to travel a distance of 600 millimeters, which is 0.6 meters. And that's about all the given information that we have thus far. We're looking for the velocity of A just before it strikes point C. So we want the velocity of A at C. Okay, we're going to use the principles of work and energy here. But in order to do principles of work and energy, we have to know the forces that are acting on these masses. So this problem's actually got a lot going on. So let's begin by looking at the forces acting on A. We have this 500 Newton force, which I'll just call F, and there's the force due to gravity and the tension at two different locations acting up on object A. Object B also has that same tension and the gravitational force m sub b times g. We don't have to worry about any x motion, but let's take a look at the sum of the forces in the y direction, and we'll start with A. So we have minus F minus m sub a g plus 2t, and that's going to equal the mass times the acceleration for A. Similarly, if we look at B, we have T minus the mass of B times G is the mass of B times the acceleration of B. And we're pushing A down, so the acceleration of A will actually be in the downward direction, and the acceleration of B will be up, so we'll put a minus sign out. The other thing we're interested in is the relationship between the acceleration of A and the acceleration of B. And if we look at the length of the rope, there's three basic lengths there. I hope that yellow shows up. But the idea here is that y sub A here and here, so that's 2y sub A plus y sub B is equal to the length of the rope. And if I do two time derivatives, I'll find that 2 times the acceleration of A plus the acceleration of B is equal to 0, which tells me the acceleration of B is equal to minus 2 times the acceleration of A. And of course that minus sign makes sense. If A is going down, B is going up, they're in opposite directions. And so I'll make a substitution into the second equation, the mass of B times twice the acceleration of A. That also indicates, since the accelerations have a 2-to-1 ratio, so do the velocities or the distances that they travel. So what's important here is that the movement of B is twice the movement of A. And what that means to us is that when A goes down 0.6 meters, B is going to go up 1.2 meters. So let's begin to look now at the energy and the work that the forces are going to apply for both of these combined masses. So we're going to look at work and energy not for any one of them, but for both of them together. So we've noticed that it all starts from rest, and that's important. So the velocities are equal to 0. So the initial kinetic energy of the system as a whole is going to be 0. Now keep in mind, 1/2 the mass of A times the velocity of A squared plus 1/2 the mass of B times the velocity of B squared. That's the kinetic energy of the system. And then we add to that the work done by the forces. But if you look at the diagram, all of the forces are constant, so it's just force times distance. So if we concentrate on A just for a moment, F here and mg are both in the downward direction, as is the displacement. So they're going to give us positive work. But the tensions are both up, so they're going to give us negative work. So I have F times delta y plus the mass of A times G times delta y, that's the work done by the force F and gravity, minus 2t times delta y. And I should subscript my delta y A. That's the work acting on A, but this is a system, so now I have to add the work acting on B. Now B, remember, is going up, so I'm going to have plus t times delta y sub b minus m sub b g times delta y sub b. Keep in mind, when A goes down a distance of 0.6, B goes up a distance of 1.2. And so delta yb is twice delta y sub A in magnitude. So I can rewrite this as t times 2 delta y sub A minus m sub b g times 2 delta y sub A. Now that becomes important because what you're going to see is that t times 2 delta ya cancels with 2t times delta ya. The 2 can be anywhere. One's positive right here, this one's negative, so they go away. Keep in mind also initially my velocities are both 0, so those terms go away. So all I'm left with is 500 newtons times 0.6 meters plus 20 kilograms, 9.81 meters per second squared, times 0.6 meters, minus 10 kilograms, 9.81 meters per second squared, times 1.2 meters. That's going to be the net work done by all of the external forces. And this will equal 1/2, remember it's a system, the mass of A, the velocity of A squared, plus 1/2 the mass of B, velocity of B squared. And so when I work that out, the left-hand side becomes 300 Newton meters. The right-hand side, I'm going to have 1/2, 20 kilograms, times the velocity of A squared, plus 1/2, 10 kilograms. Now the velocity of B, since there's a 2-to-1 relationship, this will be twice the velocity of A. Keep in mind, I square that whole quantity. So the right-hand side becomes 10 kilograms times V sub A squared, plus 5 kilograms, but then that 2 becomes a 4, so there's 20 kilograms V sub A squared, which is 30 kilograms V sub A squared. So V sub A squared equals 10 Newton meters per kilogram, which is 10 meters squared per second squared. And so the velocity of A is equal to the square root of 10 meters per second. Now the second part of the question, in part B, we're asked to solve for the velocity again, except instead of counterweight B, we're going to just use a 98.1 Newton force, which is the same as the acceleration due to gravity times the mass of B. But the main difference becomes that force is still there. This force is still there. But what we lose is this right here. There's no longer mass of B. And so the 300 Newton meters does not change. But this term would go away in that scenario. And so you'd have V sub A equals the square root of 30, because you just divide 300 by the 10, square root of 30 meters per second. So replacing the force due to gravity with an equivalent force but not the mass or the weight of the object, what you're really doing is you're taking away the mass of that object from the system, and therefore that whole thing is going to go away. Okay, here's another example. This problem is really more interesting because of the geometry than anything else. So I have a 7 kilogram block. So the mass of A is equal to 7 kilograms. There's an initial velocity of 1.5 meters per second up the incline. That's in this direction. After it's traveled up the incline, I'm going to call that delta S, 0.6 meters. We know that it has a velocity. I'll label it velocity of B, not that the pulley is moving, but I'll just call that the velocity at B, 3 meters per second. And we're interested in the work done by friction or by the frictional force exerted on the block. We neglect the masses of the pulleys. Now here's the deal. The tension is doing some work, but as we go up the incline and make it to this position here, the angle will have changed. So what we need to know is, how much work did the tension do? Well, we can get that information, interestingly enough, from this pulley right here. What I'm going to do is take note that there's a tension there and a tension there on that massless pulley, and 140 newtons down. Now the pulley has no mass, so when I look at the sum of the forces in the y direction, I get two tensions up and 140 newtons down, and that equals the mass of the pulley times the acceleration of the pulley, which I'll label the acceleration of c. Now acceleration of c is not 0, but the mass of c, that is 0. And so 2t equals 140 newtons, or t is equal to 70 newtons. Now why is that important? Because once I know what the tension is, the tension will always be in the direction of the movement of the cord. And if I can figure out how far did the cord move, and it isn't 0.6 meters, that will give me the work done by the tension. So as I analyze A, I find out that I have an mg in this direction. That's going to do some work. The normal force in this direction, that will do no work because the displacement is to the right. It's at 90 degrees to the normal force. And therefore the work, because remember that's a dot product, work is equal to F normal dot delta S. That's equal to 0. These are vectors at 90 degrees. And then I have the frictional force back this way. So I need to know how far up the incline the block has moved. That will tell me how far the rope has moved, and that's the important part here. So in gold here, I'm going to move up the incline to here. And the length of my cord, that's going to be the new length of my cord. Notice here it's 1.2 meters. The question is, what is it here? Well, the way I'm going to find this is with the law of cosines. I know, because this is 30 degrees, alternate interior angles, and this much is 15 degrees, that this must be 15 degrees in here. This is 1.2 meters, this is 0.6 meters. And so the new length of the cord, which I'll just call r squared, is equal to 1.2 meters squared plus 0.6 meters squared minus 2 times 1.2 meters times 0.6 meters times the cosine of 15 degrees. And so r is equal to 0.6396 meters. So it was 1.2 meters, so the length of the cord has changed by 1.2 meters minus 0.6396 meters, which is 0.560 meters. So, using work and energy, I can say that 1/2 the mass of A times the velocity of A at the bottom squared plus tension times delta L plus mg sine theta times delta S, and actually that's minus because mg is pointing down, minus the work due to friction. Those are the only three forces doing work. This will equal 1/2 the mass of A, the velocity at point B squared. So that's 1/2 7 kilograms, 1.5 meters per second squared, plus 70 newtons times 0.560 meters minus 7 kilograms, 9.81 meters per second squared, sine of 15 degrees, 0.6 meters, minus u due to friction equals 1/2 7 kilograms times 3 meters per second squared. When I work that out, I get u due to friction equals 4.94 joules. And that should be 15 degrees, which is what I used. Okay, here's another problem. This one involves power. I have a 60 kilogram runner, so I know the mass of this runner is 60 kilograms. and she's increasing her speed, so V initial, let me call it V1. So V1 equals 2 meters per second, and V2 equals 4.3 meters per second. And she does so in a time period, delta t, which is t2 minus t1, that's equal to 5 seconds. Now, she develops constant power. That's important. So the power is equal to a constant. I'm going to take advantage of that during the time interval. We're neglecting air resistance. We're interested in what is this power. What is the power that she develops when she does that? And what is the distance traveled? Now remember that power is equal to force times velocity, but that's also equal to mass times acceleration. So I've just rewritten acceleration as a derivative of velocity with respect to time. That's the definition of acceleration, times v, and that's equal to a constant. The reason I do that is I know that the velocity is changing in a time interval. I want to know what this constant is for power. So what I'm going to do is I'm going to write this out as mass times velocity dv. Now I only know the beginning and the ending velocity, right? That's going to equal this constant, which I'll label as c times dt. But it's a constant, so it comes out of the integral. So let's integrate both sides. And remember, we integrate from corresponding limits. So my time, I'll start at time t is equal to 0, but I started at velocity of 2 meters per second. And I end up at some time of 5 seconds, but I ended up with a velocity of 4.3 meters per second. Now my velocity is changing. Again, I don't know how that change is taking place, but it's changing. So the mass is constant. That comes out of the integral. So I get 60 kilograms times v squared over 2. Evaluate this from 2 meters per second to 4.3 meters per second. And over on the right-hand side, c comes out of the integral, and the integral of dt is just t, and so I'm going to get 5 seconds. Delta t, if you'd like. And I'm going to utilize my units when I calculate this left-hand side. So I get 60 kilograms times 4.3 meters per second squared minus 2 meters per second squared. All of this is over 2. And that's going to equal 434.7 kilograms meters squared per second squared, which of course is a joule. And then I'm going to divide that by 5 seconds. So when I do that, joules per second, that's watt. I get 86.94 watt in this 5 seconds. How far does she travel? I need an x. And so recall that acceleration, dv dt, can also be written as v dv dx. What have I done there? Recall from several weeks ago, dv dt equals dv dt times dx dx is a derivative of x with respect to x. That's just 1. But when I interchange my denominator, I get dv dx dx dt, but dx dt is velocity, and then there's dv dx. So I can do the same thing. I'm going to get a v here and a v here. So I have a v here and a v here, so that's v squared. So I'm going to get mv squared dv. mv squared dv, that's the left side of my integral. The right side, I'm going to bring the dx over here. That's the constant, but I know what that is. That's 86.94 watts. So 86.94 watts dx. And I integrate both sides from 2 meters per second to 4.3 meters per second. And so the 60 kilograms comes out. I'm left with v squared dv, so I'm going to get v cubed over 3. Evaluate from 2 meters per second, 4.3 meters per second. And over here I'm going to get 86.94 watts. That comes out because it's constant. The integral of dx is just delta x, which of course is what I'm looking for. So this is 20 kilograms, 3 going into the 60, 4.3 meters per second cubed minus 2 meters per second cubed equals 86.94 watts delta x. And so my left side is 1430.14 kilograms meters cubed per second squared equals 86.94 watts. But that's kilograms meters squared per second cubed. Okay, just go back to here. We ended up dividing this by the 5 seconds, hence kilogram meters squared per second cubed. And so the kilograms will cancel. The seconds cubed, that cancels. Meters squared cancels all but one of the meters, which is good. That's what I would anticipate, is times delta x. And so delta x is equal to 16.45 meters. And that's the distance she traveled in that time period. And if you think about it, she went from 2 to 4.3 meters per second. So we'll ballpark that at around 3 meters per second times 5 seconds. That's about 15 meters. And so that number is reasonable.